Hi everyone, I continue to solve problems on the related rates. Water is draining from a canonical tank at the rate of 2 meter cube per minute. The tank is 16 meters high and its top radius is 4 meters. How fast is the water level falling when the water level is 2 meters high? Let me first sketch the related figure. Let's have a canonical tank. Okay, something like this. And we have water inside. And this is draining. Okay. And the radius is 4. The top radius is 4. It is given in the problem. And the level of the water is 2 meters high. This is 2 meters. 2. And the tank is 16 meters high. The tank is 16 meters high. This is 16. Okay. And what else? Okay, it's all. The formula of the volume of the tank, of the canonical tank, is equal to, volume is equal to 1 over 3 pi r square radius square times height. Okay. So the question is, how fast is the water level? How fast is the water level? That is h. Falling when the water level is exactly 2 meters high. We first write down the related equation of the problem. And as you see, both the radius and height are the functions of time. Of course, the volume of also is the function of time. So before taking the derivative of each term with respect to t, it is better to write r radius in terms of h. As you see in this question, r over h, the rate of r over h is 4 over 16. 4 over 16. Okay? So r is, in this case, r is h over 4. So I will plug this expression of r in the volume formula. In this case, the volume formula becomes 1 over 3 times pi times h over 4 square times h. And this is equal to pi h cube over 48. Okay, now I think we are ready to differentiate this formula. We are ready to differentiate this formula with respect to time. So, derivative of v, that is dv over dt, is equal to pi over 48 times 3h square times dh over dt. And dv over dt is given in the problem. dv over dt is given in the problem as minus 2. Since the water is draining from a canonical tank at the rate of 2 meter cube per minute. It means the volume of the canonical tank is decreasing at the rate of 2 meter cube per minute. It means dv over dt is equal to minus 2. So, minus 2 is equal to minus 2 is equal to 1 over 16 pi 2 square. Since, look at the example again, when the water level is exactly 2 meters high, it means h is 2, that is 2 square dh over dt. So if you calculate, you will see that dh over dt becomes minus 32 over 4 pi. Okay, so the height of the canonical tank decreases at the rate of 32 over 4 pi. So it is all about the problem. We first construct the equation, we first write the related equation of the problem, and then since we have two variables of t, two variables of time, we have to write down r in terms of h. Then we continue to differentiate each term with respect to time, since each variable is the function of time. Let's look at the example 2. A ladder is sliding down along a vertical wall. If the ladder is 10 meters long and the top is slipping at the constant rate of 10 meters per second, so the question is that how fast is the bottom of the ladder moving along the ground when the bottom is 10 meters from the wall. Let me draw the related figure of this problem first. Let's say this is the vertical wall, this is the vertical wall, and this is the ground. This is the ground, and this is the ladder. Okay, this is the ladder, and this ladder is 10 meters long. 10 meters long. What else? This ladder is sliding down along a vertical wall. If the ladder is 10 meters long and the top is slipping, and the top is slipping at the constant rate, so it means, let's say this vertical line is y and the ground is x, so dy over dx, the distance of y, decreases at the constant rate of 10 meters per second. It means dy over dt is equal to minus 10. Okay, dy over dt is equal to minus 10. So what else? So it is requested to find dx over dt. It is requested to find dx over dt when x is equal to 6 meters. When x is equals to 6 meters. How fast is the bottom of the ladder moving along the ground when the bottom is 6 meters? This is 6. Okay, so when x is 6 and the long of the ladder is 10, y becomes 8. Okay, this becomes 8. What is the related equation of this problem? The relevant equation is the Pythagorean theorem, which is a squared plus b squared is equal to c squared. In our case, x squared plus y squared is equal to 10 squared. Okay, and do not forget that y and x are the functions of time. When we differentiate each term with respect to t, we have 2x times dx over dt plus 2y dy over dt is derivative of right hand side is equal to 0. I implicitly differentiate this equality. So as you see, dy over dt is given from the problem. We are requested to find the x over dt, the change in the x variable, the change in the ground. So the x over dt becomes 40 over 3 meter per second. So we plug all known values, variables in this equation to find the x over dt. It's rather simple question. Let's look at the third example. A city is of a circular shape. A city is of a circular shape. The area of the city is growing at the constant rate of 5 square kilometers per year. How fast is the radius growing when it's exactly 240 kilometers? So we have a circular shape. We have a city which is a circular shape. Okay, so circular shape, something like this, and the area, of course, the area formula of a circular shape is equal to pi r squared. The area and r, the radius, are the functions of time since they change with respect to time. So this is the area of a circle with radius r, and I and r, do not forget that, are the functions of time. The area of the city is growing at the constant rate of 5 square kilometers. So the a over dt is given. We are requested to find the r over dt when r is exactly 240 kilometers. Let's differentiate each term with respect to t. The a over dt is equal to pi 2r, the r over dt. Okay, and the a over dt is given in the problem, which is 5. Okay, 5 is equal to pi 2, r is given, this is 240. The r over dt is requested to find. In this case, the r over dt, the change in r, the change in area is given, and the change in r becomes, in this case, 1 over 96 pi kilometer per year. Okay, per year. So